Hello, everybody. Today I'm going to present some of the work that I did on one of the Capstone projects on the Coursera platform. Now I'm going to talk about the Modern Robotics Capstone project on the KUKA Youbot control. This is presented by me, Ashraf Faraj. In this project, we're going to tackle the modeling and control of a KUKA Youbot. Now, the left figure here shows the image of a real KUKA Youbot, which is made from a mobile base right here, and a 5 degrees of freedom arm installed on it with a gripper at the end. Now figure 2 here shows this same Youbot in the Copelicing simulator in which we are going to present our control results. Now the two figures here show a more detailed description of the Youbot. The figure on the left shows the Youbot base from an upper view, which shows the four wheels, which are all mechanism wheels, with an angle of pi over 4. Now these wheels allow for sliding, okay, to the side in a direction perpendicular to the robot's forward direction. To the right, we see a more detailed dimension description of the Youbot arm that is installed on top of the mobile platform. Now this right here shows a control algorithm for the full project, in which we said we're going to try to simulate a pick and place scenario. So we're going to first of all generate a trajectory offline of the whole robot motion from start to finish, including the grasping configurations and all. Now this right here would be a reference to the controller, which is going to receive an estimation of the configuration at this time step from the odometry block. Now the odometry block actually uses the configuration at an earlier time step and the wheel velocities at the earlier time step as well. The controller uses the current configuration and the desired configuration of the end effector to compute the wheel velocities at time step t. First of all, we're going to describe the trajectory generator in detail. So the problem of trajectory generation is that we're trying to find a series of homogeneous transformations xs, such that x0 is equal to x start and x1 is equal to x end. S is a function of real time that transforms the interval 0 to t. T is the whole time of the motion to 0, 1. Now xs can be written using the following equation: x start multiplied by the matrix exponential of log x start inverse with x end multiplied by s. This equation right here is based on screw theory, in which the log term actually expresses a velocity twist, which if followed for 1 second would take us from x start to x end. Now s, which is the time scale parameter, is usually chosen as a polynomial, either third order or fifth order polynomial, or even higher degrees. In this case, which shows a fifth order polynomial satisfying the following conditions, which is s0 is equal to 0, s is equal to 1, the derivatives and the second derivatives at the endpoints is 0 to ensure smooth motion. In our case, we divided the path into whole 8 segments, which were actually suggested by the project page, which I'm going to put a link for in the description box. Now, first of all, we're going to start at a certain start position. We're going to move to a standoff position. From the standoff, we descend to the grasp configuration. We hold the grasp configuration for a few time steps to ensure that the gripper actually fully closes on the object. From there, we go back to the standoff. From the standoff, we move to a place standoff, that is to the configuration right before dropping the object. Then we descend from the place standoff to the drop configuration. We drop the object and wait for a few time steps so that the gripper fully opens. Then we return to the standoff. Now the odometry section of the project will have to update the robot's configuration, especially the configuration of the mobile base. This would actually require us to have a kinematic model of the base with mechanisms. So the choice of the wheels actually affects how the wheel velocities tend to move the platform. In our case, this equation can be found easily using a few kinematic analysis. This right here would be U1 to U4. They are the speeds or the velocities of the four wheels. This matrix right here we call H, and this right here would be the velocity twist of a frame attached to the mobile base. From this, we can deduce what we would like to call the VB6, which is the six-dimensional twist that we're going to use to update the transformation. The configuration is updated using the following equation: x new is equal to the x old, which is the old configuration, multiplied by the matrix exponential of that expresses the VB6 velocity twist followed for time dt. This relationship can also be derived using the modern screw theory. Now, the goal of the controller is to move the end effector in a certain configuration trajectory. So first of all, we have to compute the end effector configuration using the following equation. The configuration of the end effector relative to the fixed space frames given by the XSB, which is the configuration of the base relative to the fixed space, multiplied by XB0, which is the configuration of the arm base relative to the base, and then X0E, which is given by the arm forward kinematics as a function of the joint variables. We then move on to compute the Youbot Jacobian, that is the full Youbot Jacobian. We do that by stacking the base Jacobian. We should, however, note that we should express this in the end effector frame. This can be easily achieved by multiplying by the correct transformation matrices. We also stack the Jacobian of the arm, which is a function of the joint variables. We then use the control law given in this equation to calculate the desired end effector body twist. Now, this equation is made up of a feed-forward term, which expresses the desired velocity twist in the end effector frame, a proportional term, which is proportional to the error twist, which is given by log of x inverse xd, and an integral term, which is ki multiplied by the integral of the error twist. Finally, we convert this desired end effector body twist to velocities of the wheels and the joints by multiplying with the pseudo-inverse of the Youbot Jacobian. Then we apply these velocities to the wheels and the joints appropriately. For the results section here, we see the KUKA Youbot in the Copelia sim, starting at a default position, moves toward the object to be grasped, lowers to grasp the object, gives time for the gripper to fully close on the object, then goes back to standoff, moves to the dropping position. When it reaches the dropping position, it lowers in order to drop the object, gives time for the gripper to open, drops the object, and goes back to the standoff configuration. Now, this right here would show a more qualitative description of the results. This is the magnitude of the error twist vector through the first 4 seconds of all trajectory motion. We can see that the magnitude of the error twist vector tends to zero quite quickly, taking nearly 2 seconds in response, and producing nearly no static error. This is due to the effect of the integrator. Now, this concludes this project in which we studied the kinematic modeling of a KUKA Youbot robot. We designed the trajectory generator for a pick and place task. We also implemented the odometry function to update the base configuration as the robot moved. We also implemented a closed-loop feed-forward BI controller and demonstrated the results in the Copelia simulator. And that's it. Thank you for listening.